So the problem is count odd even divisors. You are given an integer n and you want to calculate the number of odd divisors of n. I am properly audible, right? Uh, so first problem is count odd even divisors. You have an integer n and you want to calculate the number of odd divisors of n and the number of even divisors of n. For example, 2 has one odd divisor and 1 has even divisor. 8 has one odd divisor, which is 1, and 3 even divisors, which are 2, 4, 8. So in the test case, there are 100 test case and n is 100. So solutions of O and O n square can pass since 1E8 operations are allowed. So let's see the test cases. Just one. For one, the divisors would be just one, which is odd. So 1, 0 would be the answer. Odd and even. For 2, it would be 1 and 2. So 1 odd and 1 even. For 3, it would be 1 and 3. So 2 odd and 0 even. For 4, it would be 1, 2, 4. So 1 odd and 2 even. For 8, it would be 1, 2, 4, and 8. So 1 odd and 3. So this was the sample test case. So we know that for any number n, a divisor of n must be less than equal to n. Since divisor is a number that divides n. Basically, if n by a, if n percentage a equal to 0, then a is a divisor. So basically, divisor should be less than equal to n, since any number greater than n cannot divide n. So what we can do is we can check for every number from 1 to n. Does it divide a? Does it divide n? So the way we can check if it divides n is, so the way we can check it if it divides n or not is simply by using the percentage operator, which returns the remainder when n is divided by I. So if the remainder is 0, then I is a divisor, else I is not a divisor. And we also need to count the number of odd and even divisors. So we can just check if I remaindered by 2 is 0, then it is even, else it is odd. So the time complexity of doing this would be O of n, since we need to check for every number from 1 to n. And if it is a divisor, we need to check if it is odd or even. So I'll show you guys the code. This is the code. First, I take input the test cases, and O denotes the number of odd integers, odd divisors, and E denotes the number of even divisors. So for all numbers from 1 to n, we can simply check if n percentage I is 0. And if n percentage I is 0, then it means that I is a divisor of n. So we can check if I is even by checking the remainder by 2. So if it is even, we can E++, else we can odd++, and then see how it goes. That was the first question. So, does anyone has doubt? They can raise their hands. I'll unmute them. Okay. So let's go to the next question. Now the next question is check odd even divisors. You are given integers a and b. You want to check if there exists some positive integer n such that it has exactly a odd divisors and exactly b even divisors. So for example, 2 has one odd divisor and one even divisor. 8 has one odd divisor and three even divisors. Is it possible? You only need to print yes or no based on whether there exists some integer n. You do not need to print the value of n. Constraints are t is 10 to the power 4 and ab are 10 to the power 9. So I think log a something type of complexity needs to be, because O of a and O of b would not pass. O of square root a and O of square root b would also give problems. So I think less than that. So let's see. Problem B. So the sample test case is 1, 0. Basically, we are given the number of odd and the number of even. I think this is the order, right? First integer is a is the number of odd divisors. So we are given odd and even. So one odd divisors and zero even divisor. This simply means number one. So this is a yes, because one has just one odd divisor. Zero odd divisor and one even divisor. This is a no, because every number has the divisor one. So the number of odd divisors must be at least one. So this is our first observation, at the number of odd divisors must be at least one. Let's see the next test case. 1, 1. So we were given this example in here above, that 2 has one odd divisor which is 1 and one even divisor which is 2. So yes, again number 2, yes. Then we have 1, 3. 1, 3. So basically 3 even divisors and one odd divisor. This has the answer no, because let's try to find this number. So 3 even divisor must mean that either there are 2, 4, 8. Basically, I'll explain why this test case is no later. Let's move on for now. 3, 2. This is 1, 0, 0, 1, 1, 1, and 1, 3. Okay, okay. Oh, sorry. So for the number 8, this is yes, as 8 has 1, 2, 4, and 8. These are 3 even and 1 odd. Then 3, 2. This is no. This is basically 3 odd and 2 even. So why is this no? Let's see why is this no. Basically, any number must be represented like this. P1 to the power A1 into P2 to the power A2 into P3 to the power A3, so on till Pk to the power Ak. any number n can be represented like this, where P1, P2 to Pk are prime numbers. This is just the prime factorization of n. So since it has some even divisors, there should be P1 must be equal to 2. Since any number greater than 2 and it is a prime, it has to be odd. So all these have to be odd. Let's say that P1, P2, P3 are in increasing order. So P1 must be equal to 2 if even divisors are not equal to 0. And because P2, P3, P4 and Pk have to be odd, and any divisor of n will be of this form. Divisor would be of this form. Basically, P1 to the power B1 into P2, P2 to the power B2 till Pk to the power Bk, where B1 is less than equal to A1, B2 is less than equal to A2, Bk is less than equal to AK. Because divisor need to divide the number n, so A1, B1 should be less than A1, so that when we divide, it is something, it has something like this happens. P2, A2, Pk, AK, and when we divide, K, P. So since B1 is less than A1, this would become A1 minus B1, this would become A2 minus P2, this would become AK minus Pk. So hence this number will be a divisor. So for a divisor to be even, it must have B1 not equal to 0 and P1 equal to 2 for a divisor to be even. Since P2, P3, P4, P and Pk are all odd, since 2 is the only even number, even prime, so P1 must be equal to 2 and B1 must not be equal to 0 for a divisor to be even. So basically what we conclude from this is for every divisor of the form P2 to the power B1, P3 to the power B3 into P4 to the power B4, Pk to the power Bk. Every divisor that has this form, basically where B1 is equal to 0, these are all odd divisors. For all these, there would be P1 corresponding, A1 corresponding even divisors. So for every odd divisor, there will be A1 corresponding even divisors. How? Basically, let this number be some x. So now we know x is an odd divisor of n. So P1 is, since P1 is 2, 2 to the power 1 into x, comma 2 to the power 2 into x, till 2 to the power A1 into x. These all will also be, these will be the even divisors. So for every odd divisor x, we get A1 even divisors. This is our second observation. So if a number has two, if a number is even, let's say this is even, then for every odd divisor of that number, there will be A1 even divisors, where A1 is the power of 2 in prime factorization of n. This is our second observation. This first line is because if a number is not even, then it would obviously have 0 even divisors. So if a number is even, then for every odd divisor of that number, there will be A1 even divisors, where A1 is the prime power of 2 in prime factorization of n. So basically, what this means that the number of even divisors equal to number of odd divisors into A1. And since we need to tell that a number exists such that it has A odd divisors and B even divisors, so we can control the A1 of this number. So hence the even divisors number of must be a multiple of odd divisors. Number of odd divisors. So this is the reason why 3-2 was a no. As 3 odd divisors, for 3 even divisors, there cannot be 2 odd divisors. For 3 odd divisors, there cannot be 2 even divisors. Since number of even divisors must be multiple of 3. So another way we can prove this point is that, let's say some number has odd divisors as A and even divisors as B. So what I can do, I can make that number equal to 3 to the power A minus 1. So now the number will have 1, 3, 3 square till 3 to the power A minus 1 as its divisors. And these are A. And what I can do is multiply 2 to the power some t such that A into t equal to B. Because for all these odd divisors, there will exist, let's say, we'll pick one from this and let's call it 3 to the power x. So there will exist 3 to the power x into 2 to the power 1, 3 to the power x into 2 to the power 2, and so on till 3 to the power x and 2 to the power t. So we'll have t even corresponding to each one of these. So total we'll have A into T odd, A into T even, corresponding to each A we had T odd divisors, T even divisors. So in total we'll have A into T even divisors. So this was the solution to the question. Basically, let's use the property number 1. The number of odd divisors must be at least 1. And then if a number has even divisors, then even divisors must be multiple of odd divisors. And okay, if a number doesn't have even divisors, that is b equal to 0, then we can simply just say that n is 3 in 3 to the power a minus 1. This will give 1, 3, 3 square to the power a minus 1. This will give the odd prime factors or divisors. Sorry. A odd divisors. I forgot A odd divisors. So it is always possible to construct a number with just a odd divisors. It would be 3 to the power e minus 1. So basically the solution would look like this. If number of odd divisors cannot be 0, number of odd divisors is a, so if a is 0, then no. If a and b both are 0, then also no, because I mean, yeah, it is contained in this only. So let's give this. If a is 0, then no. If a is not 0, if b is 0, then yes. And if both are not 0, then b must be a multiple of a. Even divisors must be a multiple of number of odd divisors. So b percentage a should be equal to 0, then yes. Else no. We put else if. So we can see this on the sample test case. For 1, 0, a is 1 and b is 0. So here, yes. For 0, 1, a is 0, so no. For 1, 1, 1% 1 is 0, so yes. For 1, 3, again 3% 1 is 0, so yes. For 3, 2, 2% 3 is not 0, so no. 2% 3 is not 0. This is equal to 2. So this was the solution to this question. I'll show you guys the code. Basically, write into the test case A, B, C in A, B. And if A and B both are 0, then no. If just B is 0, then yes. If just A is 0, then no. This condition was kind of unnecessary. I could have put this at the top. So if A is 0, then no. If B% A is 0, then yes, else no. So the time complexity of this would be O of 1, actually O of T. Each test case in O of 1. So that was the question number 2. Does anyone have doubts? I was discussing problem B. Check odd even divisors. You can raise your hands if you have doubts. You guys can raise your hand if you have doubts. So I think it is clear to everyone. Let's move on to the problem C. Problem C. Given a one-index permutation P of the integers in the range 1 to n, you will construct an array A of the size n, where AI is equal to Pi plus I. Now let f of P as the number of distinct elements in the array A. For example, P equal to 3, 4, 1, 2. The constructed array A is 4, 6, 4, 6, and thus f of P is equal to 2. So basically 4 and 6 show 2. Given integers n and k, find a permutation P in the range this with f of P is equal to k. Answer always exists under the given constraints. So the constraints are n and k are up to 100 and t is 100. So O of n and O of n square can pass, I think, because 1 operations can be done in a second. Time limit is 1 second. So the question is, if I am given a permutation, let's say P1, P2 till Pn, I'll construct another array A corresponding to this permutation such that P1 plus 1, P2 plus 2, Pn plus n. Now, f of t is equal to number of distinct elements in A. So basically number of distinct elements in this. And in the question, I need to find permutation P, find P such that f of P is equal to K. So let's see the test cases. First is n equal to 1. N equal to 1, K equal to 1. So basically, for n equal to 1, there is only one permutation. P would be like this, and A would be 1 plus 1, 2. So, yes, A for this, K is equal to 1. So, yeah, this would be the answer. Second test case is 2, 1. So, for permutation 2, it can either be 1, 2 or 2, 1. So, if we take 1, 2, this would give us A as 2 and 4. And this would give us A as 3 and 3. So since we need K equal to 1, this would be the answer. 2, 1. For the next test case, 2, 2, we would have this as the answer, 1, 2. For the next test case, 4, 2, we have answer 3, 4, 1, 2. Basically, if I add 1, 2, 3, 4 in this, it becomes 4, 6, and 4, 6. So 2. H 2. And next is 6, 3. Answer for this is 6, 3, 4, 5, 2, 1. 6, 3, 4, 5, 2, 1. 1, 2, 3, 4, 5, 6. And the A would be 7, 5, 7, 9, 7, 7. So 1, 2, 1, 2, 3. A equal to 3. Hence, this is the answer. So basically, I observed one thing here. Here in this test case, 2, 1. And for this 2, 1. Basically, what happens is for any index I, you add I in the array A, in the array P, and for the index I plus 1, you add I plus 1. So if this index is X and this index is X minus 1, then this would be X plus I and this would be X plus I. So basically something like 5, 4, 3, 2, 1 would become same in the array A. You can see if I add 1, 2, 3, 4, 5 in this, it becomes 6, 6, 6, 6, 6, which is every element becomes same when I put them in decreasing order. So since we need K, and what happens if I do not change the order and just keep the permutations as 1, 2, 3, 4, 5? I'll add 1, 2, 3, 4, 5 to all the elements and it will become 2, 4, 6, 8, 10. So we will have K different elements. Sorry, N different elements. Since all these are in increasing order and these are also in increasing order, there cannot be any same numbers because this function is also increasing and this function is also increasing. So the sum of two functions would also be increasing. So every number in this would be distinct. It would be greater than the last. So this would contain n different elements. So what I can do is, if I need to create k elements, k distinct elements, I know one thing, that the numbers, these numbers are in increasing order. So 8 cannot be found anywhere before it, and 10 cannot be found anywhere before it. That's how there are n distinct elements. So if I need to reduce these number of distinct elements, I need to form these chains. These chains which result in the same number in the array A. So what I can do is, if I had 1, 2, 3, 4, 5, and I add 1, 2, 3, 4, 5 to it, I get 2, 4, 6, 8, 10. But if I swap these, if I make it 2, 1, 3, 4, 5, and then I add 1, 2, 3, 4, 5, then it becomes 3, 3, 6, 8, 10. So this reduced, here we had 5 distinct, and now here we have 4 distinct. Now what if instead of just doing 2, 1, if I do 3, 2, 1? So this will become 4, 4, 4, 8, 10. Now I'll have these 3 and 3 distinct elements. So we kind of see the pattern being made here, pattern that is being made here. So what we can do is, if we need k distinct elements in the answer, for k distinct elements, we can select the first few numbers and arrange them. If they are 1, 2, 3 to some x, we can arrange them like x, x minus 1, x minus 2 till 1. And after that, we'll let the numbers be like they were. So this would be x plus 1, x plus 2 till n. Now, the thing is, basically, any number that is here, this would be, when I add 1, 2, 3 in this, 1, 2, 3 till some x, then x plus 1, x plus 2 till n. These numbers would be x plus 1, and this would be 2x plus 2. So this would always be greater than this, and this would be 2x plus 4, and this would be 2n. So these numbers would always be greater than them. So these are all same, and these are all distinct. So since I need k elements distinct, I need to make the count of these as k minus 1, and I'll keep the rest of the elements here. So let's find out x. Basically, total number of elements is n, and here I have x elements, and here I have k minus 1 elements. So n must be x plus k minus 1. So x comes out to be n minus k plus 1. Let's check if this is true or not. Let's take some example as n equal to 5 and k equal to 3. So x comes out to be 5 minus 3 plus 1, which is 3. So that means I'll do 3, 2, 1, and then 4, 5. So this would be my p, and the corresponding a would be, I add 1, 2, 3, 4, 5. So this becomes 4, 4, 4, and then 8, 10. So basically we can see that this number is x plus 1, x plus 1, and this number is 2x plus 2, 2x plus 2. And there are 3 distinct numbers. 3 distinct, 4, 8, and 10. So basically, since these are in increasing order, they must be all distinct. And these are same because I reduce one here and one here is increased. So the sum remains constant. This is plus 1, and this is -1. So the sum remains a constant, but here it is +1 here and +1 here as well. So sum would always be increasing. So this way we proved our solution to be correct. So what we can do is for the solution, find x, which is n minus k plus 1, n minus k plus 1, and then basically this becomes the answer. This uh, we just make this permutation x minus 1 till 1, and then x plus 1, x plus 2 till. So we can construct this permutation in O of n. So the total time complexity would be O of n. I'll show you guys the code. This is the code ln c in nk. So basically, start is the variable x, which is n minus k plus 1. And answer in the vector answer, I would store the answer. So what I'm doing is for I equal to 0 till I less than n, or start becomes 0. So I put answer of I as start and decrement start each time. So basically, if I try run this, start for the same n equal to 5, k equal to 3, x becomes 5 minus 3 plus 1, which is 3. So initially my answer array is 0, 0, 0, 0, 0. Answer of 0 becomes the value 3, and I make the value 3 as my 2. Then answer of 1 becomes 2, and then answer of 2 becomes 1, and then start becomes 0. So when start becomes 0, I exit out of this for loop, and then I set start as n minus k plus 2, which is nothing but n minus k plus 2 is nothing but n minus k plus 1, which is x plus 1. So I am putting x plus 1 here. I'm trying to put x plus 1 here. So I'll start from this index I plus 1. Basically, I stored the value of index where this for loop exited. So I'll start from this index and I'll increment start each time, and I'll put the value of answer I as start. So this becomes 4, this becomes 5. So this is my final answer, which we got above as well. So that was the problem C. If anyone has doubt, they can raise their hands. I also came up with an idea, partially, but not able to complete, where I am lacking. Are you talking about this question, C, Santosh, or you're talking about last question? Uh, well, this question was kind of, there can be multiple solutions to this question, I think. So even your idea might lead to a solution. You just need to practice more. Uh, if anyone has doubts in my solution, they can raise their hand. Okay. So let's move on to the question D. The D is max tree minimum. You have a tree with n vertices. A tree is a connected, undirected, acyclic graph on n vertices with n1 edges, n minus 1 edges. You want to assign distinct labels to the vertices of the tree. You will choose a permutation p of the integers and then assign the vertex x a label of px. Okay. Define max of S for a set S as the minimum non-negative integer not present in S. For example, this. Define FUV as the max of Px1, Px2, Px3, where x1, x2, x3 are the vertices on this simple unique path from U to V. X1 is U, xk is V. Define the scores of the tree as sum over all f of x comma y. That is sum of f over all pairs of vertices. Okay. You must find the minimum possible value of score if you can suitably choose the permutation P. Okay. The constraints are number of vertices is less than equal to 2000 and sum of vertices does not exceed 2000. So at max n square solution can pass. Problem D. Basically in this problem, I have a tree with n vertex and I need to give value to each vertex where P1, P2 to Pn is a permutation. And here permutation means numbers from 0 to n minus 1. So P1, P2, Pn, P1 is the value of vertex 1. Pi is value of vertex I. Pi is value of vertex I. So I need to give them values such that all of the values form a permutation. And I need to give the values in such a way such that the summation x equal to 1 to n and y equal to x to n f of x comma y is minimized. So I need to minimize this. I need to give the value of permutation in such a way that I minimize this and I need to find the minimum value of this where f of x comma y is in the tree. Let's suppose the path from x to y contains the vertices u1, u2, u3 till uk. Let this be path from x to y in tree. So basically, in tree, a path between two vertices, there is only a unique path between two vertices, so this would be unique. And f of xy is max of this. Now, what is max? So max of basically here we have some examples 1, 0, 2, 0, 2, 3, 4. So max is basically minimum excluded number. So the minimum positive number that does not appear in the given set is the max of that set. So for this set, we have 0, we have 1, we have 2, but we do not have 3. So max of this would be 3. And another example is max of 1. Max of 1 would be 0 since we don't have 0 in this set. So that is max. And f of xy is the max of the set containing all nodes all nodes in the path x to y. Actually, the value of these nodes. Max of the values of these nodes in the path from x to y is f of xy, and we need to minimize the summation of f of x comma y. So let's see the test case. First test case is 1, 2, 2, 3, and 3, 4. 2, 2, 3, 4. So basically, the sum would become f of 1 comma 1 plus f of 1 comma 2 plus f of 1 comma 3 plus f of 1 comma 4 plus f of 2 comma 2 plus f of 2 comma 3 plus f of 2 comma 4 plus f of uh, plus f of 3 comma 3 plus f of 3 comma 4 plus f of 4 comma. These are the values, and we need to minimize this sum. So let's start with putting 0. Let's start with assigning the value 0 in these vertices. So uh, let's check one by one. What happens if I assign 0 to this vertex? If I assign 0 to this vertex, basically every path that does not contain this vertex would not have 0 in its set, and all the f of xy is basically max of p of u1, p of u2 till p of uk, where this u1, u2, uk is the path from x to y. So any path that does not contain 2 would have its max as 0, since 0 would not be in that path. So f of 3 comma 3 becomes 0, and f of 3 comma 4 becomes 0, and f of 4 comma 4 also becomes 0. F of 1 comma 1 becomes 0, and I am left with these f of 1 comma 2, f of 1 comma 3, f of 1 comma 4, 2 comma 2, 2 comma 3, 2 comma. Basically, non-zero max would be of these paths. Let me read all of these paths will have non-zero. This, 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 and this and this. These paths would have non-zero max. So basically, what is happening is whenever I set some vertex 0, let's say there is some tree and I set one of its vertex as 0, then every path through that vertex now will have some max. Like this, this could be a path, 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 and all these paths passing through vertex 0 would have some max. So placing 0 in the middle is not optimal. What I can do is, if I place 0 at a position like here, now all these paths go away. Now these paths do not contain 0 anymore. There is only one out of these paths that contains the 0. So basically in this case, 1, 2, 3, 4, if I had placed the 0 here, I would only get these paths with non-zero max. These paths would be gone. This were just extra. So basically it is better to place 0 at a root node. Root nodes are basically a node that is connected to one that is connected to exactly one other node. A special leaf one other node. So basically, putting 0 at a leaf node gives us very little number of paths. Otherwise, if I had put 0 somewhere here, all the vertices on the right side of this and all the vertices on the left side of this, all these would have given a pair with all these. But if I put 0 at the extreme of the path, so I would now only have vertices on the right side of it. Since a leaf node only has one single node attached to it, so all these paths would not be multiplied. All these, there is only one side to it. If there was some node like this where it had 5 nodes here and 6 nodes here, so 5 into 6, 30 paths would have been there. Since from every node here, I could have gone to any node here. So there would be 5 into 6, 30 paths. And plus, there would be these 6 and these 5. And but if I had placed the 0 at some root node, there is only one direction I could go in. So if there, let's say there are 6 nodes here, or maybe 11 nodes actually, 11 nodes here. So now I only have 11 paths. 11 plus 1 self path, if you take that. So placing the 0 on a leaf node is optimal. That gives us with very less remaining paths which are non-zero max. So now we have fixed the position of 0. So that must mean that for this test case, either 0 comes here or 0 would have gone here. And since this is a symmetrical tree, I can just take any of that, any one of those positions. So if I place 0 here, should I place 1 here or 1 here or 1 here? If I place 1 here, again I would have many paths from 0 which have 1 in their path. Basically, this path would have max 2, this path would also have 0 and 1, this path would also have 0 and 1. So that increases our max from 1 to 2. If I have 0 and 1 in my path, suddenly now my max would be greater than equal to 2. Since I already have 0 and 1, now max becomes greater than equal to 2. We don't need this. We need to minimize the sum of max. So what we should do is place 1 again on a leaf node, so that there is only one path from 0 to 1. Sorry, I need 1 here. If I place 0 on a leaf node and 1 on a leaf node, there is only one path from 0 to 1. Basically, let's take some bigger tree. You guys will understand there better. This is big enough. So what happens here is I must put 0 at some leaf node. So let's say I put 0 here and I put 1 again at some other leaf node. Let's say I put 1 here. So now how many paths will contain both 0 and 1? There is only one path. Whereas if I had placed let's say 0 over here, there would have, let's say 0, I have placed 0 over here. There would have been this path, this path, this path. So basically I would get multiple paths with 0 and 1 in them. So I should place 0 and 1 on the leaf nodes, so that there is only one path between 0 and 1. There is just only one path which contains both 0 and 1. Since the path has to start from here and it has to end here only, so that 0 and 1 are included in the set. So basically now what we have gotten in the problem, we have gotten one single path, one path which have both 1 and 0, and f of 0 comma basically n paths, I should say n minus 1 paths, actually n minus 1 paths with just 0. since any other path other than this one path would have only 0 in it, and 1 would not be there. So basically the max of all these paths would become 1. Also, rest paths do not have 1 and 0. So these paths would have max as 0. This path would have max as 1. And this path can have any max. We'll see that. So let's say max of this is t. So basically our answer becomes for n minus 1, it is 1. So n minus 1 paths, it is 1 and 0 for the rest. And t for the last path, basically this path. Now, if there exists, basically if there is just a single node, let's say that these nodes didn't exist. These nodes didn't exist. So there is just one node outside this path. What I can do is I can give this node the value 2. So now the max of this path would be 2, since the set of this path would not contain 2 as it is outside this path. So the max of this part would become 2. 0 and 1 are present and it would become 2. So t would be 2. But so basically, if there is a single other vertex outside of this path, so I can give that vertex the value 2 and the max of this path would become 2. So t becomes 2 and the total answer would become n plus 1. But what if this node also was not there? So now all the numbers must be here, like 2, 3, 4, 5, all the numbers must come here. So the max of this would become n. So t would become n. In that case, the answer would be n minus 1 plus n. 2n minus 1. We cannot go any lower than this. In this case, let me prove that. Basically, this is for the cases where the tree is like this. Because only in these cases I would have 2 leaf nodes and the path between them is the whole tree. If there is even one more branch here, then I would have set the value of this as 2 and then I would have gotten the answer as n plus 1. So we are proving this, that the best answer we can get is 2n minus 1 is because it is obvious that I would be putting 0 here so that the least number of paths have 0 in it. And I would be putting the number 1 here so that the least number of paths have both 0 and 1 in it. I cannot put anywhere 1. I cannot put 1 here because then this would also have 1. This would also have 1. This, and this. That is a loss. We only have this path. We can only do only this path. So it is better to put 1 here. Now there is only one path which contains both 0 and 1, and the max of that obviously would be equal to n. So and all of the other paths would have 0 in it. So the max of that would be n minus 1. Sorry, n minus 1 paths and max of it would be 1. So n minus 1 plus n. So that would be 2n minus 1. And in all the other cases, let me prove that the minimum max would be n plus 1. So what I'm doing is 0, 1 and 2 here. And I can put any numbers here. So non-zero maxes would be this, and this. So all the max other than this, other than the 0 and 1 path, this path, all of them are 1. So there would be n minus 1 ones plus this last path would have max 2. Since 2 is outside of this path, 2 cannot be inside this path. So I'll have to. So n plus 1 would be the answer. And this is optimal because uh, this is the least we can go. Since we are doing this summation x equal to 0 to n, y equal to x to n, f of x comma y. Let's say some vertex I has 0, has the value 0, and some vertex j has value 1. So basically, uh, my laptop crashed, I think. So I have to restart. Sorry guys, some error occurred in between. So basically, I was in the middle of doing that for a tree like this. The best answer I get is n plus 1. And if it has just one more branch, then the best answer, sorry, 2n plus 1, 2n minus 1. And the best answer for these cases would be n plus 1. Since if I put 0 here and 1 here, I proved this case. I just need to do this case. If I put 0 here and 1 here, I can put 2 here, and then there would be n minus 1 paths from 0 that have the max 1, and there would be a single path which have the max 2, so n plus 1. So basically, we cannot go any lower than this because we need to calculate I equal to 1 to n, j equal to, sorry, x equal to 1 to n, y equal to x to n, f of x comma y. And let's say the vertex I has value 0 and the vertex j has value 1. So if the vertex I has value 0 and j has value 1, then basically in this summation, there must be n paths that start from I or end at I. Basically, I to 1 and I to 2 and I to 3 and so on for I to n. Basically, there would be n path that start from I, and one of these would be, let's just write it separately. F of I comma j. Let's just suppose that f of I comma j is not in these. It is there. So all of these values would have max at least 1, and all of these value and this value would be at least 2. At least 2. So since this is at least 1, the sum of this would be n minus 1, and this is at least 2. So this would be 2. So basically, for a subset of these values, for just the path starting from ith node, I get the answer as minimum n plus 1. So if I take all of the values, the answer must be greater than equal to this f of p. F of p must be greater than equal to n plus 1. So basically, the smallest value f of p can have is n plus 1. And in the cases where the graph is not a linear graph, where the tree is not a linear tree like this, it must have at least 3 roots, because 2 roots would be on the path, on the straight line, and there must be at least 1 branch from here that would give at least 1 root. So in the cases where there are, I'm saying root, I mean leaves. So in the cases where there are greater than equal to 3 leaves, the answer would be n plus 1. And if there are just 2 leaves, the answer would be 2n minus 1. And I've proved for both the cases that it cannot be any lesser than this. So I'll show you guys the code now. Let's test this on the test cases. First test case is 1, 2, 2, 3, 3, 4. 1, 2, 2, 2, 3, 4. For this, the answer would be n plus 1, 2n minus 1. Since it is a straight tree, it would be 7. And the next test case is 1, 2, 1, 3, 1, 4. 1, 2, 1, 3, 1, 4. The answer for this would be n plus 1, which is 5, which is again correct. So this was the question. Let me show you the solution. So basically, I have maintained, I should have written name leaves, but I don't know why I'm using roots today. So basically, ignore this name. I'm taking CNN, and then since I'm maintaining the tree as a global vector, so I'll have to clear it each test case, and then I take the n minus 1 edges and input, make it an undirected tree. So if g of I dot size is 1, that means the current node is connected to only one other node, then it is a leaf. So I push back it, and if there are just two, there cannot be just one single leaf. There have to be at least 2. So if there are 2 leaves, then the answer would be 2n minus 1. Else there must be more than 2. So the answer would be n plus 1. That was the solution for this question. So if anyone has doubts, they can raise their hands. Wait, my screen was not shared. If anyone has doubts, they can raise. Can you explain the 2n+1 power function? So, 2n-1. Do you mean 2n-1? Okay. So basically, for a tree like this, if anywhere there is a path, there will be always will be f of x comma y like this. Basically, let this be the vertex x and this be the vertex y. Then f of x comma y would be n. Since this contains all the nodes and these are a permutation of 0 to n-1. Permutation of 0 to n-1. So f of x comma y would be n, because a permutation of 0 to n-1 would have max equal to n. So for this path, the value is n, and there would be at least n-1 other paths that start with a 0. Let's suppose we have a 0 here, then from this 0 to every other node, 1, 2, 3, 4, and itself as well. So if the 0 is in between, then there would be n paths. And if the 0 is here, then there would be 1, 2, 3, 4, and itself. And we do not count this whole path because we have already taken it here. So if the 0 is at an extreme position at a leaf node, then there would be n-1 paths that start from 0, because we don't count this. We have already counted this. And these n-1 paths would have at least greater than equal to 1 max. So just from this path and n-1 other paths that start with a 0, we get f of p greater than equal to n plus n-1. Greater than equal to 2n-1. So we cannot go any lower than 2n-1 for a tree like this. Did you understand that? Was my screen shared? Yes, it was. So if you have any doubt, you can type or raise your hand. I'll unmute you. So I think it is clear. Sir, any hints on solving your thought of parity to mainly one max you can take into secondary? Well, E is a little bit difficult to discuss here since only 4-5 people solved it, I think, in diff 2. Priority heap and min heap. No, sir. For me, still I have to practice me. I could only first two. I understand that. I think if you are talking about this approach, you must mean you're talking. I think you were talking about this question, shop game, both mini and maximum. So it had only 3 solves in diff 2, so I don't think I should discuss it here. If you have any doubts in A2D, you can ask. Uh, uh, no, sir. Did you understand the solutions now after the discussion? Okay, cool. What was the possible rating of mint tree? Uh, mint tree, I think it should be 1600 CF. Yep, I think it should be 1600 CF, probably. Okay, so I think you guys don't have any more doubts, so I'll end the meeting. Thank you.